All right, welcome back. MC312 Thermal Fluid Systems 2. This is video 2 of our ideal gas relationships lesson. We left off video 1 with deriving our generic equations for entropy change of an ideal gas, our equations 6.32 and 6.34. And we did that by applying our Gibbs equations, our knowledge of our change in internal energy and change in enthalpies for an ideal gas, and lastly by applying our ideal gas equation of state. So we're going to build on those two equations by now deriving specific equations for change in entropy of an ideal gas with the constant specific heat assumption and an equation if we are assuming variable specific heats. And then we'll close out this video with developing our isentropic processes for an ideal gas and applying those relationships for constant specific heat or a variable specific heat. So let's get after it. Let's do a review of our objectives for our roadmap for success for today. So we've been applying our ideal gas equation of state, our objective 1, throughout this process. Now we're going to finish out lesson objective 2 and then close the video out with lesson objective 3. Okay, let's start off with deriving our equation for our change in entropy for our ideal gas, Ig, with the constant specific heat assumption. And again, like I covered at the end of the last video, it is okay to make the constant specific heat assumption depending on the temperature range that you're dealing with, the type of gas that you are dealing with, decision that you would make, and it would be given to you as an assumption for problem-solving purposes. And it is the easier of the two to derive our equations for, so we'll start with that for today. And remember, we left off last video with our two generic equations for our change in entropy. So I'll just remind you of those. So our change in entropy, state 1, or state 2 minus entropy at state 1 is equal to the integral from 1 to 2 of our specific heat at constant volume, change in temperature divided by the temperature, plus our universal gas constant divided by the molecular weight, times the natural log of our specific volume at state 2 divided by the specific volume at state 1. And for tracking purposes, we said this was equation 3, and in your book, it is equation 6.32. Okay? And then the other form of this, which we derived using Gibbs equation number 2, was our equation number 4. Entropy at state 1, or sorry, state 2 minus state 1 equal to our integral from 1 to 2 of our specific heat at constant pressure, temperature differential divided by the temperature, minus, in this case, the universal gas constant divided by the molecular weight, and again times our natural log of our pressure at 2 divided by our pressure at 1. And the book has this listed as equation 6.34. Okay, so using those, we can start off for deriving our entropy, change in entropy equations for constant specific heat. So if we're saying our specific heat at constant volume and our specific heat at constant pressure are not a function of temperature, then our equations 3 and 4 above will simplify to equations 6.38 and 6.39. And you can find those in your book. And that is our entropy at state 2 minus our entropy at state 1, which is equal to our specific heat at constant volume times the natural log of our temperature at state 2 divided by temperature at 1, plus our last term on the right-hand side of equation 6.32. And this is equation 6.38. And by applying our constant specific heat assumption, it allowed us to simplify the integral on the first integral on the right-hand side of our equation 6.32. By having a constant specific heat at constant volume, we can pull this term outside the integral and simply use our knowledge of our logarithmic, our natural log term, and simplify our derivative of temperature divided by temperature to our natural log of temperature at state 2 divided by temperature at state 1. Okay? And applying the same simplification to the first integral on the right-hand side of equation 4 gives us our equation 6.39. Entropy at state 2 minus entropy at state 1 is equal to our specific heat at constant pressure times the natural log of temperature at state 2 divided by temperature at state 1 minus universal gas constant divided by the molecular weight times the natural log of our pressure at state 2 divided by our pressure at 1. And this is equation 6.39 in your textbook. And these are getting the red cloud of importance. Please understand how we got to these forms of the equation. And for further reference, we'll say it's equation 5 and equation 6, respectively. All right. So pretty straightforward for our constant specific heats, but now let's look at how this changes for our variable specific heats. So our change in entropy for an ideal gas with our variable specific heats. Now we have to introduce a new term, and that is going to be introducing our reference state. Our S degree at temperature T is what this reference state refers to. And this is introduced on page 6-10 in your textbook. And you will get these reference state S degree at temperature T from tables 8 or 8 echo or tables 9 or 9 echo. And what this is doing is allowing us to simplify that first integral on the left-hand side of equation 6.32 or 6.34 as we see here. And because we are not assuming constant specific heats, we can't pull that outside the integral. But if we have a relationship between the specific heat at constant volume and temperature and the relationship between the specific heat at constant pressure and temperature, we can come up with our reference state. And that is what we'll use to simplify that integral in equation 6.34 and 6.32. So that reference state is our, as I mentioned, our S degree at temperature T. So what does that look like written out? So our S degree at temperature T, and by definition, is equal to the integral over T ref, our reference temperature, to T, specific heat at constant pressure, times our differential at T divided by our temperature, and that is equation 6.35. And the book does a great job of deriving this and showing how this S degree at temperature T is equivalent to our integral and how it cancels out of our specific heat at constant pressure or constant volume. And so you could look through that derivation and again on page 6-10 if you'd like to. But we'll substitute this into our equation 6.32 to get our final form of equation 6.37. And so we'll call this equation D. And if I substitute D into equation 4, we'll get equation 6.37. So putting equation D into equation 4, which we developed in video 1 and I introduced at the beginning of this video. And that will give us this form of the change in entropy equation for variable specific heats. So that is now equal to our S degree at temperature T2 minus our S degree at temperature T1 minus our universal gas constant divided by our molecular weight times our natural log of pressure 2 divided by pressure 1. And this is equation, again, 6.37 in your text. And for our reference here, calling that equation 7. And it's getting the red cloud of importance. So again, we introduced this reference state, S degree at temperature T, to allow us to simplify this integral here. I'm going to underline it in blue. This first integral on the right-hand side of equation 6.34. And we can simplify it to now using our reference state, S degree at temperature T, which we would look up in our tables 8 or 8 echo if we're using air, or tables 9 or 9 echo if we have an ideal gas other than air. Okay? So now we've derived our equation specifically for calculating our change in entropy for variable specific heats and constant specific heats, depending on the assumptions you're making and the convenience of your problem. So now let's finish out our video and our final lesson objective by talking about the isentropic process for an ideal gas. And we're going to develop some relationships that we can use to solve our ideal gas problems. And we're going to have different relationships for a constant specific heat assumption or the variable specific heat assumption. And we're simply going to be looking at, in this case, for our derivations, the process from 1 to 2s. Remember, we use the 2 sub s to denote an isentropic process. And recalling what an isentropic process is defined by is we have an adiabatic and reversible process happening. That's what we call an isentropic process. So if we have a reversible process, we have entropy change is equal to 0. So our change in entropy is equal to 0. We also know that our universal gas constant, R bar divided by molecular weight, is equal to the difference in our specific heat at constant pressure minus specific heat at constant volume. And we can also use our K, which is the ratio of specific heats, constant pressure to constant volume. This comes from equation 1.58 and equation 1.59 in your text. Okay, so first let's look at our isotopic relations for constant specific heats. So from equation 5 and 6, if the process is isentropic, so again, our change in entropy is 0, we have a reversible process, we get the following isotropic relations. First, we can relate our isotropic pressure at isotropic state 2 divided by the temperature at 1 equal to the specific volume at 1 divided by the specific volume at state 2 isentropic. All of that raised to our specific heat ratio K minus 1. This is equation 6.50. Next, we can also use our ratio of isotropic temperature at state 2 divided by the temperature at 1 to relate our pressures. So we have our temperature ratio is equal to our isotropic pressure at state 2 isentropic divided by pressure at 1. And all of that raised to our specific heat ratio, K minus 1 divided by K. That's equation 6.52. And our last isentropic relation for our constant specific heats, we have our ratio of pressures. Pressure at state 2 isentropic divided by pressure at 1 equal to our ratio of specific volume at 1 divided by the specific volume at state 2 isentropic raised to our specific heat ratio K. And that is equation 6.53. And these will become useful once you know 3 of the properties. You can find the 4th, and you could solve and work through your ideal gas problems with the constant specific heat assumptions. Remember, these are only for constant specific heats. That's why we have our K value, or our K, which is our ratio of specific heats, again, at pressure divided by specific heat at constant volume. So let's look at our isotropic relations for variable specific heats. And for this, we'll be looking at equation 7. So from equation 7 and applying the isentropic assumption, so for our change in entropy equal to 0, isentropic, first introduce 2 new convenience functions. The first is relative pressure, or P sub R. And the second is relative volume, or V sub R. And these are simply, as I say, convenience functions to use in the derivation of our 2 isotropic equations for variable specific heats. And you can find the values of both of these relative pressure or relative volume for air only, and that will be in table 8 or table 8 echo. Okay, so let's write out our 2 variable specific heats isentropic relations. The first in terms of our relative pressures and isotropic pressure at state 2 and pressure at state 1. So we have our ratio of relative pressure at state 2 isentropic divided by the relative pressure at state 1, which is equal to our pressure at state 2 isentropic divided by our pressure at state 1. This is equation 6.46 in your text. And the second will be our isotropic relation in terms of our volumes. So first we have our ratio of the relative volume at state 2 isentropic divided by the relative volume at state 1 equal to our specific volume at state 2 isentropic divided by our specific volume at state 1. This is equation 6.48 in your text. And remember, this is only for, these two relations are only for variable specific heats of an ideal gas, and you're going to find your relative pressure or relative volume in table 8 or 8 echo. If you'd like to look up the exact definition of our relative pressure, you could find that on page 6-15. It's equation 6.45 in your text. And the relative volume you can find on page 6-16, and it's equation 6.47 in your text. We will go and look at our tables next so we can all be on the same page and understand where we're getting these values from. Here we have table 7. So this is going to be values of ideal gases other than air. This is where you're going to come to get your specific heats. Table 8 will be all your properties and values for your ideal gas of air at different temperatures. And again, you can see where we have our properties that we've talked about, some new ones today. So our S degree at temperature T. We also have our relative pressure, P sub R, and our relative volume, V sub R here. And remember, this is only for, tabulated only for our ideal gas properties of air, and only applies for our isentropic relation. So when our change in entropy is equal to 0. Lastly, let's look at table 9, which is our ideal gas properties of selected gases other than air, right? So we have our H bar, U bar, and S degree at temperature T bar. So these are all on a molar basis. So it's important to understand that's where the bar comes from. And you look at the units, we have kilojoules per K mole. All right, so pay attention to that when you're using those in your problems. Of course, let's do a review of our 312 reference sheet. So find where we have equations that we developed today. So under our ideal gas block, we have our ideal gas equation of state, which is familiar from 311 and we use extensively today to do our derivations. So again, using the constant specific heat assumptions, we have certain equations associated with that. So we have our constant specific heat block and our variable specific heats block. You can see we have our associated change in entropy equations and our isentropic relationships. Remembering that for constant specific heats, we have a K value, which is our ratio of specific heats, using those for our isentropic relations. And then our change in internal energy and our change in enthalpy equations should be familiar from your MC311 RDC, and simply equal to the specific heat at constant volume times change in temperature for change in internal energy, or the specific heat at constant pressure times change in temperature for change in enthalpy. Some new concepts are variable specific heat. So now we have our S degree at temperature T, which we get from table 8 or 8 echo, depending on the unit system we're in. But remembering that for an ideal gas, our internal energy is still only a function of temperature, and enthalpy is only a function of temperature. Next, just to reiterate our isentropic relations for variable specific heats and applying to our ideal gas of air only, we have a ratio of our relative pressures and relative volumes. And remember, you can find both of these values tabulated in table 8 or 8 echo. Okay, this closes us out for the ideal gas relation lesson and the end of video 2. I appreciate everyone's attention. And just a reminder, if you'd like to see the full derivation of the equation for the changed entropy of assuming variable specific heats, you can see that in section 6.5.3 of your text. And then if you want to see the isentropic processes derived for both constant specific heats or variable specific heats, find that in section 6.6.3 of your text. Have a great day.